making a bunch of choices. So let me talk about the lifting properties. Of chains of projective modules. Okay. So here is what I'm gonna prove. So here's a lemma. Or maybe I could just draw the picture first. Okay. So what we can do is we can start with a morphism, m to n, right? So this is just a morphism of R modules, right? And if I have a projective resolution, right here, so this is a projective resolution. Okay, and then if I have any resolution here, so this is Q0, Q1, Q2. So this is any resolution. Right? What happens is that I can, so using the property that, so let's call this one epsilon, and this one eta. So I can extend this map like this. So I can extend this to a cochain map, right? So we can extend this situation. This a cochain map. We can extend, let's say, F to a cochain map. Okay, so if you're just given morphisms and then resolutions, you can actually fill in the arrows, right? This is kind of the key property. So let me just say this again. So theorem is, so let M and N be R modules. Okay, and we're going to let F from M to N be a morphism of R modules. Okay, and then we're going to let P to M be a projective resolution. Okay, so what does it mean for it to be a resolution? It means that this is so it's an exact sequence, and it agrees the zeroth homology is just like the homology of, it's just M, right? So I guess this is exact here. So this needs to be surjective. Okay, then so the theorem says, so for any resolution, so not necessarily projective, Q bullet to N, right, there exists a chain map lifting, so the chain map, let's do this here. F bullet from P bullet to Q bullet, lifting F bullet. So in the sense that that this diagram holds, this commutes. Okay. Moreover, this is unique. This map is unique. Up to chain homotopy equivalence. Okay, so it's like you have these morphisms, they extend to the resolutions, and the extension is unique up to homotopy. Okay, so let's do the proof. Okay, so proof. Okay, so there's kind of two parts of this proof. There's the existence part, and then there's the uniqueness part. So there's the existence part. Okay, so so kind of the base case, and so we will do this by induction. Okay, so all right, so we're going to do this by induction on n, and we're going to show that all the maps. So if you have the maps up to a certain point, that you're going to have all the maps. You can construct the next map. Okay, and so the case, so the kind of the base case is the case n is equal to -1, where we set the original map f to be f minus 1. Okay, so we're going to call this map here f minus 1. Okay, and then this map is going to be f0, f1, f2, and so on. And so what we're going to do is we're going to suppose that they exist up to a certain point, and then we're going to show the next one exists. We're going to show that, yeah, I'll write this in. So let's do the inductive step. Okay, so suppose we have fi for I less than or equal to n. Okay, so here we'll have Pn, Qn, we have Fn. So we have maps like this. Okay, Qn minus 1. So Pn minus 1. Fn minus 1. Okay, so we have all these maps up to here, and all right. All right. So the first claim here is that I can kind of truncate this. So what I'm going to do is I'm going to want to split this up into two pieces. Okay. So the first observation is that this induces a map on cycles. So this induced map on cycles. So we're going to have a map here from Zi. So we're going to have maps Zi from P bullet to Zi of Q bullet. Okay, and so recall that. So here, let's just recall what this means. Zi of any complex. So this is the kernel of the map from AI to AI minus 1. So the things that go to 0. BI, by the way, so these are the cycles. These are called cycles. And then the boundaries, just for, by the way. So this is the image of AI plus 1 to AI. And so these are the boundaries. And then homology is cycles modulo boundaries. Okay. All right. So okay, so we're going to have a map from the kernel of one to the kernel of another. So why is this? Okay, so what we have is if dA is equal to 0, right? Then so notice that d of f of a. So because it's a chain map, it commutes f of d of a, right? Which is f of 0, which is 0. Okay, So this implies that if dA is equal to 0, then d of f of a is equal to 0. Okay, so this is why you have a map on cycles. Okay, and so this thing allows us to break up. So this observation allows us to break up star. Okay, so here is star. Okay, and here's how we're going to break it up, right? So first, we can break it up. The first piece goes like this. So I'm going to truncate. Okay, so this goes to Qn, Fn. This is Fn minus 1, Qn minus 1, like so. And then we have Z, Z and Q. Okay, Q bullet 0 like this. Okay, and then we have this map here, F tilde n. So what is F tilde n? So here, so F tilde of n. This is just F restricted to, Fn restricted to the cycles. Okay, so the restriction of the map Fn. Okay, so this is the first part we have. The second part we have is, and so this is, notice that the rows are exact on this thing. So so on this thing, rows are exact. And in particular, this injects, so Zn injects into there. So it's a submodule. Okay, so the other way to break it up is to do the following, right? So we have Pn plus 1, right? This goes into, so Zn P bullet, right? And this goes to 0. So Q Qn G like this. Okay, so I guess this is saying that this is surjective. So should this be B? One moment. Here's the proof over here. Okay, so we have this map like so. Is this doesn't this isn't surjective, so do we need it to be surjective? So okay, so what we're trying to do is we want to apply the universal property of P being a projective module. Okay, so this is, so we kind of have like two pieces. We have this piece and we have this piece here. Okay, so let's look at this piece again, the bottom piece. And so the strategy is to apply projectivity of Pn plus 1 to lift the map, to get a map Pn plus 1 to Qn plus 1. Okay, so let's write this out. This doesn't feel exact on the rows here. So let me say that if we want this to be correct, I think we need B like this. Okay, so this works. This is definitely surjective now if I do it like this. And so do we have that it maps boundaries to boundaries? Let me check this. So yeah, so let's check that this map actually makes sense. So do we have a map from boundaries to boundaries? So if so D of A, if I apply F to that, oh yeah, so this is df of A. That's true. So boundaries do map to boundaries. Okay. So also, Bn p bullet to Bn q bullet. Okay. Okay, so this map is surjective, and now this diagram here, right? We can write as so we set it up to look like our universal property. Okay, so what do we have? So we have a map here, Pn plus 1. Okay, and we have a map Qn plus 1. And this goes to surjects onto B in Q bullet like this. And this thing maps to here by taking the composition of the two maps. So this is, I guess, Fn tilde prime. Okay, so and Fn tilde prime is the restriction, is equal to Fn restricted to Bn p bullet. Okay, so we have this. So this thing here is you apply D first, and then you do Fn tilde prime. Okay, okay, so this is a surjective map of modules, and you have a map from a projective module. So this implies that we can fill this in. So this is here. Okay, and this map is the D map. Okay, and so this is in. So this thing here uses the universal property. Or the lifting property of projective modules. So this kind of lifting property. Right. So surjections lift to surjections. Okay. So so yeah. So this is a surjective map. So it can lift. All right. So now so now we have this map, and let's check that this map is a. So let's check that this map is a chain map. Okay. So all right. So what do we need to check? So we need to check that so we need to check that after introducing this Fn plus 1, that it commutes the way we wanted it to, right? So we want, again, An plus 1, or we called it P. Pn plus 1, Qn plus 1, Qn, Pn. So we want this to commute.
Since the BNs are subsets of the PNs, that doesn't just automatically become that then?
So since the BNs, yeah, exactly. That's exactly what happens. That's exactly what happens. Yeah, yep, exactly. So yeah, that's exactly what happens. So yeah.
You just don't have to write the restriction anymore for the F, yeah.
Yeah, exactly. Yeah. So what do you write? So we have so what do we want to check? So FND, right? Fn plus 1D. So we saw that was Fn tilde prime D, or let's see, what did we Oh, sorry, I wrote this the wrong way. D. Right. So this is Fn tilde prime D. And so this is the same thing as FND because it's already going into the boundary, right? So these two maps have the same effect. Yeah, and that's exactly what you're saying about inclusion, right? Okay, so then next time I'll do uniqueness. So this shows that the map exists. I'm a little worried because I don't seem to have used this part here, but I'll think about this. Yeah, and then I'll do the next part next time. So thanks for coming.
Great, thank you.